Okay, good morning. So our goal is to transform complex Haskell programs to simple Haskell programs. And what is the reason? Well, there are many reasons for that. One reason is we want to define the semantics of Haskell. We have done that already for simple Haskell. And in order to do it for complex Haskell, we won't extend the definition of our semantics, but instead we give a translation from complex to simple Haskell. And in this way, we can also say the semantics of a complex program is the semantics of the corresponding simple program. The other reasons for doing this transformation is that later on we want to implement Haskell. We also want to do type checking for Haskell. And again, we will only do this for simple Haskell. And then we can say, well, if we have a complex program, then first we would translate it into a simple program in the way that we will define now. And then it's enough to define everything just for simple Haskell. Now, the main thing that is missing in simple Haskell is pattern matching. And in order to get rid of pattern matching, we need some new predefined functions, which I defined in the last lecture. And the predefined functions are, well, we need one function which is always undefined. I call this bot. And then for every data constructor, we need two functions, isA and argof. isA checks whether the argument is built with this constructor. So if this constructor is defined as follows, it goes from type 1 to type 2 to type n. So it takes n arguments, and then it gives you back something of this type. Then if you apply isA constructor to an object of this type, it tells you whether this object is built with this constructor or not. So it gives you a Boolean back. And similarly, argof, well, if the argument is built with this constructor, then it gives you back the tuple of the arguments. So it's a tuple where the first component is of type 1 and the last one is of type n. And we need something similar for tuples. We need, well, this is a shorthand. We want is a function for empty tuples, for tuples with 2 components, 3 components, 4 components. So we need functions isA n tuple. They take an n tuple and they give you back a Boolean, checking whether this is an n tuple or whether it's undefined. And these selection functions, they take an n tuple and they give you back the ith argument. So it's an n tuple like this, and you get back the ith argument. And our goal was to go from complex Haskell to simple Haskell. And we will do this by defining 12 transformation rules. And then we can apply these transformation rules. We can apply them in any order. And the outcome will be a simple Haskell program. Now, I will illustrate this with the append example. So this is the definition of append list concatenation. And you can see it's not simple Haskell due to many reasons. One reason is that in simple Haskell you may only have one single declaration. Here we have 2. And moreover, on the left-hand side you may only have one variable. So not something like append is applied to 2 patterns, nil and z. And so the first step, what we can do is we can transform this into a lambda expression. So the first rule of our calculus does the following thing. Instead of having 2 declarations like this, we now only have one. And then the right-hand side, and then the left-hand side is just the name of this variable. The right-hand side starts with a lambda, and since this is a binary function, this lambda takes 2 arguments, x1 and x2. And now all the declarations are transformed into one big case expression. Now, as you might remember, a case expression takes, here we take an expression, and there we have a lot of patterns. So if the first pattern matches this expression, then the result is the stuff that is behind the first arrow, where the variable z is instantiated by this pattern matching. If this pattern does not match, then we check the next pattern, and if this pattern matches the expression, then we bind the variables in this pattern, x, y, and z, according to the matcher, and then the result is this over here. So in general, the rule that we use here looks as follows. We had this in the last lecture as well. The rule looks like this. This is rule 1, and it tells us how to transform function declarations into one single pattern declaration. If we have many declarations like this, so this is like append applied to nil and z equals this expression, and append applied to cons x, y, and z equals another result. then instead we can build this new expression where we just have this variable on the left-hand side, then we get a lambda expression, and here we have a big case expression. So if these new arguments, x1 to xn, if they have the form pattern 1, 1 to pattern 1n, then the result is x1, and if they have the form pattern k1 to pattern kn, then the result is xk. So this is the first rule, and if we apply this rule, then we only have pattern declarations, and for every function there's just one pattern declaration. So there is one for append, and if we have other defined functions in our program, well, then we have more. So now let's this append program further. So currently we are at this point. Now this, of course, is still not simple Haskell. And what is the reason? Well, again, there are many reasons. One reason is already this lambda. This form of lambda is not allowed in simple Haskell. In simple Haskell, the only thing you may do is you may have lambda expressions where there is one variable after the lambda. So what we have to do is we have to get rid of lambda expressions like this where you have many patterns after the lambda. So rule 2 is a transformation of lambda expressions with several patterns. So in general, such a lambda expression with several patterns would look like this. You would have one lambda and many patterns, and here you have one expression. And now the question is, we want to replace this expression by some other expression where you don't have many patterns after the lambda. And now luckily this is not very difficult. You can easily do this by saying, well, we take a new lambda expression. Here we have just one pattern, and then here we get another lambda expression, and again just one pattern after the lambda, and so on. And then finally here we have a lambda expression, again with just one pattern after the lambda. And of course we only do this if n is greater or equal than 2. So this just means instead of writing several patterns after a lambda, we can use many lambdas and, well, one lambda for every pattern. So this is rule 2 in our transformation calculus. If we apply it here, this means instead of having one lambda in front of x1 and x2, we take two lambdas. So the result will be this. So we get from here to there by taking, well, here we have just one x1 after the lambda, and then we add another lambda in front of the x2, and that's it. So this is not very surprising or complicated. Now, in this example, we are lucky because after the lambdas, we have only variables. In simple Haskell, we may not have patterns behind the lambda, but only variables. So the question is, what happens if we have a real pattern there, not just a variable? So this doesn't occur in our example, but in general this can happen. So assume we really have something like this. Where pattern is no variable. So it is a different pattern. So how can we transform this into a lambda expression where we have a variable after the lambda? Any idea? So what we want is we want something like this. We want to start with something like this. And var is a new variable. Now, I mean, we use a similar trick that we used in Rule 1. In Rule 1, we wanted to get rid of pattern matching in several different declarations, and we did this by introducing case. Now this thing is also pattern matching. If you apply this lambda expression to another expression, then what happens is it is checked whether this expression that you apply it to has the form of this pattern. So pattern matching takes place. And, well, we have to get rid of pattern matching in the end, but we don't want to introduce many, many rules for all the different kinds of pattern matching. We only want to introduce rules which get rid of case. So we transform this form of pattern matching into a pattern matching with case, and then we just have to treat, well, we have to eliminate this case construct. So if we want to use a case construct here, then what we can do is we can do the following thing. We can say if this expression is matched by this pattern, then we return exp. So this thing does exactly the same as this, but now again, the pattern matching is encoded with case, and we have only a variable after the lambda. So this doesn't occur in our example, but in general it could occur. So this is a way to get rid of these patterns after the lambda. How we get rid of these cases, yeah, that's something we have to look at now. Okay, so what do we do next? So the next thing is we want to get rid of case, and in order to do that, to make life easier, we first transform case into some intermediate construct. This construct does not exist in Haskell. We just introduce it during our transformation, and then we will eliminate it again. So this construct will not remain in our final program. We will eliminate it finally again, but it makes the formulation of the transformation rules easier. So I will continue with the rules on this board, and I will say something about this intermediate construct on the other board. So what the transformation rules do is, the transformation rules as you can see, they transform all pattern matching into case constructs. So they first transform all pattern matching into case constructs. Then next, they transform all case constructs into these intermediate constructs that we only introduce for the transformation. And this construct is called match. So transform all case constructs into match constructs. And match does not exist in Haskell. This is only needed during the transformation, and this match will be eliminated again. So this is only needed during the transformation, and then finally we will eliminate all match constructs. So this what this match construct does is the following. Match takes 4 arguments. So match takes a pattern and an expression, and the idea is match checks whether this pattern matches this expression. If the pattern matches this expression, then the result is expression 1, and otherwise it's expression 2. So match takes these 4 arguments, and the meaning is if the pattern matches the expression exp, then the result is exp1, and in exp1 the matcher is applied. So during this matching from pet to exp, a matcher is computed which instantiates the variables in pet, and this matcher is also applied to exp. So the variables of pet may appear in exp1. So this is x1 instantiated by the matcher. And otherwise, the result is x2. So if you want to have an example, so for example, something like match cons xy, this is a pattern. And the question is, does this match cons 0 nil? If it does, then the result is, say, suc of x, and otherwise it is, I don't know, bot. So if you have something like this, then the question is, does this pattern match this expression? And if it matches this expression, the result should be x1. But in x1, the x1 would be instantiated by the matcher. Well, you can easily see that this pattern does match exp. And to match it, you have to instantiate x with 0 and y with nil. So the result of this expression will be suc of 0, because x will be instantiated by the matcher. So it would be suc of 0. This would be x2, so if this pattern would not match this expression, then the result would be bot. So in other words, we will now use this match construct. In other words, we will first transform all case constructs into match constructs. So how can we transform a case construct into a match construct? Well, let's look at our example. How would we do this? Here, we would have to find out, does this pattern match this expression? If yes, then we return this. If no, then we look at the second clause over here. So that's the idea how you can transform case into match. Maybe I first write down the general rule, and then we will do this in the example. Okay, so rule 3 also has a name. So rule 3 was the transformation of lambda into case, or transformation of lambda patterns into case constructs. And now rule 4 goes from case to match. So transformation from case to match. So if we have a case expression which looks like this, so we want to check, is this expression matched by pattern 1? If it is matched by pattern 1, then the result should be x1. And if it is matched by pattern 2, then the result should be x2. And if it is matched by pattern n, then the result is x n. And now the question is, how can we reformulate this construct with this new match construct? Well, in the match construct, the idea is, so we start with match. So we first write down the first pattern. So what we do is we want to check, does pattern 1 match this expression? If pattern 1 matches this expression, then the result is x1. So if pattern 1 matches x, then the result is x1. And otherwise, we check whether pattern 2 matches this expression. So the last argument of this first match is another match expression where we check whether pattern 2 matches exp. And if it does, then the result is exp2. And if it does not, then we have another match expression, so this continues. And then finally, the last match expression checks whether pattern n matches exp. If it does, the result is expn. And if it does not, then none of these patterns here match this expression, and then the result is undefined. So then the result is bot. So this is a reformulation of this case construct using match. And with this match, the remaining transformation rules can be formulated particularly easily. So let's do it here. How would the result look like? It would look like this. So we replace this case construct by match. So what happens? In this case construct, we would first have to match this pattern to this expression. So if this pattern nil z matches the expression x1, x2, then the result is the thing that is on the right-hand side of the first arrow. So it's z. And if it does not match, well, then we have to look at the second pattern, and therefore we get another match expression. So if the second pattern, cons x, y, and z, matches our expression x1, x2, then the result is the thing that is on the right-hand side of the second arrow. So it's this cons term. And otherwise we get bot. So by rule 4, we now have this form for our append function. And now the remaining rules deal with getting rid of pattern matching. And now we know that all pattern matching is transformed into match constructs. So by the rules 1 to 4, we can be sure that there is no other pattern matching except for these match constructs. And so now the question is, how do we get rid of these match constructs? And well, to do this, we look at the different forms of patterns. So patterns can have different syntactical forms, and for every syntactical form, we have one new transformation rule, which helps us to eliminate this. Okay, so how does that work? Now, what we do here is we match tuples. So in our example, we have a tuple pattern nil z, and we match it to an expression x1, x2, which is also a tuple. So the question is, how do we eliminate pattern matching if you have tuples? Now this is not rule 5, but rule 9, because the rules 5, 6, 7, and 8 are easier than rule 9. Therefore, I ordered them in this way. But I will present them in the order that I introduced them in the example. So the next rule that I will present is rule 9, and rule 5, 6, 7, and 8 will also come later on. So rule 9 is, so these rules 5 to 9, they deal with eliminating this match construct. And since in our example the first problem is how to get rid of tuple patterns, I will present this rule first. So this rule deals with eliminating this matching if we have non-empty tuples. So we somehow have an expression like this. A non-empty tuples of pattern 1 to pattern n. We want to check whether this tuple pattern matches an expression exp, and if it does, the result is exp1, and if it does not, then the result is exp2. Now the question is, how can we get rid of this? And here n is greater or equal than 2. So it's really a non-empty tuple pattern. How to get rid of a match with the empty tuple, we have a special rule for that later on. Now, I mean, we want to transform this into an easier problem. Now, if you think of the semantics of pattern matching, what will happen? If we want to know whether this tuple pattern matches this expression, the first thing is we have to check whether this is actually a tuple of n components. It could also be completely undefined. If it is completely undefined, then this pattern matching will also give an undefined result. If this is not undefined, and if this is really a tuple of n expressions, then what we would have to do is we would first match pattern 1 against the first component here. If this works, then we take the instantiation which was computed by this matcher, apply it to the remaining patterns, and then we look whether this instantiated version of pattern 2 matches the second component, and we continue until we have checked all n components. And if they all match, then we are lucky and we can return expression 1. And if this fails somewhere, we return expression 2. Now this is the semantics that pattern matching should have, and in order to get the semantics, we have to write down the right transformation here. So luckily, we have some predefined functions. Now this is the first. In order to get rid of pattern matching, we need these predefined functions. So what we do is we will first have to check whether this is really a tuple of n components. Now how can we check this? Luckily, we have a predefined function is a n tuple. Here we need it. So if this thing is really an n tuple, then we can continue and then try to match pattern 1 against the first component of x, and pattern 2 against the second component of x, and pattern n against the last component of x. If this is not an n tuple, we return x2. Now, if this is a well-typed expression, and this is not an n tuple, then the only thing that can happen is that this is undefined. If this is not well-typed, we need this transformation also for type checking, and that's also one of the reasons why we need this if expression over here. If this is not an n tuple, but maybe an n plus 1 tuple, then this sub-expression will be not well-typed, and our type checker will later find this out. So there are many reasons for introducing this condition. Now, okay, let's assume this is an n tuple, so it has n components. Now, what do we have to do now? We have to match pattern 1 against the first component of this. Now, how can we do this? So what we have to do is we have to match pattern 1 against the first component of x. How do we get the first component of x? Well, luckily, we have our predefined functions, and so we have also these selector functions. And these selector functions can give us the components of a tuple. So here we need component 1. So we take the selection function, which works for n tuples, and which gives us component 1. And so we now match pattern 1 against the first component of exp. If this works, then we have to continue and have to match pattern 2 against the second component of exp. And again, if this works, we have to continue. And finally, we match the last pattern, pattern n, against the last component of x. Now, and if all this works, so all these matches of pattern 1 against the first component, pattern 2 against the second component, pattern n against the last component, if all this works, then the result is x1. Now, if everything has worked, but in the last step the matching fails, then the result is x2. And, well, here, if it has worked in the first step, but it does not work in the second step, then again, the result will be x2. And if it also already fails in the first case, again, the result is x2. So if this fails at some point, then the result is always x2. And if it succeeds for all components, then the result is x1. And now you can see in this way, we can get rid of all tuple patterns. We can apply this rule repeatedly, and then finally, these patterns are no tuple patterns anymore. Otherwise, we would again apply this rule. So how does it work in our example? So in our example, it looks like this. Now, this transformation is meant to be executed automatically. So this is not meant to be readable for humans, at least not the intermediate steps. The final result of the transformation is very readable. It's a very natural looking definition of append, but the intermediate steps are rather ugly. So what has happened here? Now, to simplify this in reality it's a bit more complicated than this, because what I eliminated here are these is-a n-tuple conditions. To make this a bit more readable, I said, well, I know that these are already n-tuples, so I only wrote down the part after then. I did not write down this if-then-else expression to make it a bit more readable. So if you forget about this if condition, then you would get this result here. So let's look at this first match expression. You would have to check whether whether this tuple is a tuple of two components. So is a two-tuple applied to x1, x2? If this is true, then the result would be this match expression here. And now I already evaluated this because I know that a tuple of two components is a tuple of two components. And then the result is this. So what we do is we will first match the first component, the first pattern, against the first component of x1, x2. So we first match nil against the first component of x1, x2. If this succeeds, then we match the second pattern, z, against the second component of x1, x2. And if this all succeeds, we return the z over here. So the z is expression 1 in our rule. And if things fail somewhere, then we have to return expression 2, and expression 2 is this thing, it's the second match construct. So here we now match the first component of the tuple, cons xy, against the first component of x1, x2. If this works, then we match the second pattern against the second component here. So we match z against the second component of x1, x2. And if this all works, we get cons x, append yz. And if things fail, we get bot. So we get here, if the first pattern nil matches, but the second does not match. And we come here if already the first pattern matching fails. So if already nil does not match this expression over here, then we come here. Now, of course, you can see that this sub-expression and this sub-expression are identical, so you get quite a big blow up by this transformation, but at least it works. Now, of course, you can make this a bit easier. If you look at this, you can simplify the sub-expressions a bit. I have already simplified this is a two-tuple, and I didn't write it on the slide. And you can simplify things further. So if you want to select the first component of this tuple, x1, x2, well, the first component is x1. If you want to know the second component of this tuple, it will be x2. So to write it down in a more readable way, I will replace this. I will replace this cell expressions by x1 or by x2. So I do this simplification to make it a bit more readable, because otherwise it will be hard to understand the remaining things. So let me do this simplification, and then it looks like this. Okay, so this is our current state. This is our append program. So the append program mainly says now, first match nil, try to check whether the pattern nil matches x1. If it works, try to check whether the pattern z matches x2, and if it does, then return z. And if not, then do this here. And if already this nil here does not match x1, then you have to go into this case, and then you check whether cons xy matches x1, whether z matches x2, and if this all works, you return this thing over here. And if this again fails, then the result is undefined. So what is the next step? Well, we can now try to eliminate more of these match constructs. Now, there is no match where we try to match tuple patterns. What we still try to match is, for example, we try to match variables. So we have expressions like this. Here we match a variable z to an expression. So the question is there an instantiation of z such that the result is x2. Now, matching of variables always succeeds. We know that if we have a pattern that is just a variable, then the matching will always work. And so we can really eliminate all these match constructs where the first argument is a variable. If you want to match a variable, this will always work. So we can replace this by, in this case, by cons x append y z. But of course, we have to instantiate this z by x2, because the matcher here will instantiate z by this expression. So to do this, we introduce rule 5. So rule 9 gets rid of non-empty tuples, and rule 5 gets rid of matches with variables. Okay. So this is rule 5. Match of variables. So assume we have a match expression where the first argument is a variable. So we want to check whether the variable matches this expression. If it does, the result should be x1. If it does not, then the result should be x2. Now, we know every variable matches everything. So this variable will match this expression. So what should be the result? Well, it should basically be x1, more or less. But of course not quite, because, I mean, the matching has some effect. Now, in our example, this is the variable z, and z obviously matches this expression, but x1 contains z. So in x1, we want to replace z by this expression. So how can we do this? Of course, we could write down x1 where all occurrences of this variable, all three occurrences of this variable are replaced by x. But we don't need to do it like this. We can do this in a more elegant way. We can instead write the following thing. We can write a lambda expression, which looks like this. Now, what will happen if you try to evaluate this? If you evaluate this, this is a function which takes a variable and gives you back x1. And if you apply this function to exp, what you will get back is x1, but all three occurrences of this variable are replaced by exp. That's exactly what we want. So what this is this evaluates to x1 where all three occurrences of var are replaced by exp. So let's see why this works. So if we follow this rule, and let's, for example, see what happens with this match expression. Now, this match expression by this rule would be transformed into a function which takes a z, lambda z, to this expression. So z is mapped to cons x append y z, and this function is applied to x2. So it would look like this. So it's a function lambda z goes to cons x append y z, and this is applied to x2. Now, if you evaluate this expression, what will be the result? The result will be the thing after the arrow, but all occurrences of z will be replaced by x2. So in other words, if you evaluate this, thing, lambda z goes to cons x append yz. If you evaluate this applied to x2, then you get cons x append y x2. Right? That's the meaning of lambda expression. Lambda expression means apply this function to an argument, and then you get the thing on the right-hand side, but you replace the z's by this argument. So this is what you get. And that's exactly what we want. If you do this matching, that is what happens. You try to match this variable against this expression, which means you instantiate this variable by this expression, and you give back this third argument as the result. So we can just transform this into a nice lambda expression, and we can do it in the same way for this other match expression as well. So according to this rule, here we take a z, we return the third argument, we return z, but this z is instantiated by x2, so in other words, we get this lambda expression over here. Okay, so this is what we can do. Now, if we want to make it more readable, then so if I want to make it more readable, it would look like this. Yeah. So this is the result that we get. So this is the result that we get. We replace this first match construct by lambda z goes to z applied to x2, and we replace the second construct by lambda z goes to this const term applied to x2. And if you evaluate these lambda expressions, you would get x2 here, and you would get this const term down there. Okay, so now we have got rid of pattern matching with tuples and of pattern matching with variables. That's already quite good. Now what else? What other patterns do we have? Well, another possibility, another very simple possibility, which is similar to matching of variables, is matching with the joker pattern. Now this does not occur in our example, but in general it could occur, so we need a rule for this as well. So matching of the joker pattern, and then the original match construct would look like this. Now how could we simplify this? Now, well, matching of a variable against an expression always succeeds, and we know what the result is. Now, matching of a joker pattern against an expression always succeeds as well. And what will be the result? Only x1. Now, this is a very simple. So here no instantiation of x1 takes place. Normally, if this is a real variable, then whenever this variable occurs in x1, we have to instantiate it appropriately. But if we have the joker pattern, this will not be instantiated. So this is really just x1, nothing else. Okay, so this is a very simple rule, but it does not occur in our example. Now, the next rule is matching of constructor terms. Now, you can see in our example, we have to match nil against x1, and we have to match cons xy against x1. So the question is, how do we deal with this? So maybe I erase this over here. Okay, so this is rule 7. Matching of constructor terms, or match of constructors. So what happens if we have an expression like this? We want to match a term that is built by a constructor applied to pattern 1, pattern n. We want to match this pattern against x. If it works, the result is x1. If it doesn't work, then the result is x2. Now how can we, and we have two occurrences of this problem in our example. We want to match nil against x1, I think, and we want to match cons xy against x2. I think. Yes. No, against x1 again. So how can we do this? Now, if you look at the way we dealt with in the tuple case, when we want to match tuple patterns, now we have to match constructor terms, constructor patterns, and this works in a very similar way. So how did we do it with tuples? This is rule 9 up there on the board. Well, we first checked whether this expression is really an n-tuple, and if it is, then for every component we check whether pattern 1 matches the first component of x, pattern 2 matches the second component of x, and so on. And we needed the two predefined functions, ISA to check whether it's an n-tuple, and cell to access all these components. And now here we do something very similar. So what would you say? How do we have to start here? Now, for example, imagine we have cons xy, and we want to check whether cons xy matches a certain expression. And the first thing is we have to check, does this start with cons? If it starts with nil, then matching should fail. So how can we find out whether it starts with cons? Now this, yeah. Mm-hmm. Right, that's what we need this is a cons for. So as above, we now ask, does this thing start with this constructor? And if it starts with this constructor, then we have to check whether pattern 1 matches the first argument of this constructor and pattern n matches the last argument of this constructor. If it does not start with this constructor, then we return x2. Okay, now assume it does start with this constructor. Now we have to check whether pattern 1 matches the first argument, pattern 2 matches the second one, and pattern n matches the last argument of the constructor. How do we do this? How can we access the arguments of this constructor? Well, we need this function arcof, obviously. What does arcof constr return? It returns a tuple. So if we apply arcof constr to this expression, it returns a tuple of n components, namely the n arguments of this constructor. So what we do is, we now have to check whether the tuple of these patterns here, pattern 1 to pattern n, whether this matches the arguments of the constructor in exp. And if it does, then the result is exp1, and if it doesn't, the result is exp2. So that's it. We get the arguments of constr by this predefined function. That's a tuple of n components. And so we have to match this tuple of n patterns against this tuple of n components. And how to get rid of this tuple? Well, we know how to do this. Then we have to apply rule 9 again. So matching with constructors can be reduced to matching with tuples. And matching with tuples, we already know how to get rid of this. Okay, so we have to do this now. In our example, and this looks like this. Now, to make life easy, I replace these lambda expressions. So I write x2 instead of lambda z arrow z x2, and I write this const term instead of this lambda term. And then if I do this, the following happens. So then the following happens. Now let me see whether I can. Oh, this looks horrible. Okay, ignore what is written there at the moment. What is written by hand there, and I will explain this in a moment. So what do we get? Now, instead of checking whether, instead of having match nil x1, we now check whether, we now get the following expression. If x1 is a nil, so if is a nil x1, then we return what happens next, and otherwise we get this into the second case. So if x1 is a nil, then we continue, and otherwise we go into the second case, which is the const case. Now what happens if we continue? What we do here is we get a match with the arguments of this constructor. Now nil is a constructor of arity 0, so it has no arguments. In other words, here we get the empty tuple. So the empty tuple is now matched against the arguments of this expression. So the empty tuple is matched against arc of nil of x1. And if this works again, then we get x2. Now, if something fails, then we go into the second case with cons. And how does the second case with cons look like? Now, we used to have cons, match cons xy, and then here we had x1. Now, instead, we check whether x1 is built with cons. So we get if x1 is a cons. If this works, then we have to take the arguments of the pattern, so x and y, and we have to match them against the arguments that we have in x1. And if this all works, we get the result as before, and if it doesn't work, we get bot. So, of course, this sub-expression here is the same as the sub-expression over here. So, by applying this rule, we get the thing that we have up there. Now, let's try to make this a bit easier. If we want to make it easier, then we can, of course, try to get rid of this match with the empty tuple. Now, this is the only thing we didn't have up to now. We have all other kinds of pattern matching we have treated by now. We have pattern matching with variables, with the Joker pattern, with constructor terms, and with non-empty tuples. But a match with the empty tuple, as we have it up there, we did not treat yet. So we need another rule, Rule 8. And Rule 8 is there to deal with pattern matching with the empty tuple. So, how does the matching with the empty tuple work? So, what happens if we have match the empty tuple against an expression? If it works, you get x1. If it doesn't work, you get x2. Now, this works almost as in the case when you have a non-empty tuple. So, you first check whether this is really a tuple of arity 0. So, if is a 0 tuple exp, if it is, well, now life is a bit easier because normally for non-empty tuples you now have to look at all these patterns inside the tuple. Now here we have no pattern inside the tuple. If this is a tuple of arity 0, then pattern matching works. No variables are instantiated, so the result is simply exp1. And if it doesn't work, then the result is exp2. So this means in our example, we could replace this match expression here by if this thing over here is an empty tuple, then we return x2, and otherwise return the stuff that is down there. So if arc of nil x1 is an empty tuple, then we return x2, otherwise return something else. And now to simplify this further, I will replace this thing by x2, because if x1 is not undefined, then this thing will always, and if this is well typed, then this will always be true, and we get x2. And in our example, this cannot be undefined, otherwise this is a nil would already fail. So whenever we reach this point, x1 is indeed an empty, arc of x1 is indeed an empty tuple. So to simplify this in the presentation, I will write x2, because otherwise this will become completely unreadable. And now if you have this, then you have the following thing. You check whether x1 is nil If it is, you return x2. Otherwise, you check whether x1 is built with cons. If it is, then you try to match this tuple xy against the arguments of the cons in x1 and return this, and otherwise you get bot. And now, to transform this further, we have to apply the remaining rules again, because here we have a match of a tuple pattern. Now, as I said, matching with constructor terms is transformed into matching with tuples. So now we have to apply the rules, the rules 9 and the rules 5. Well, the rules that we had up here. And if we do this, then we will finally arrive at this algorithm. And this is now the final outcome of the transformation. And this is indeed simple Haskell. So append is now defined as follows. Append takes two arguments, x1 and x2. It checks whether x1 is a nil, so whether x1 is empty. If it is, then it returns x2. Otherwise, it checks whether x1 is built with cons. If it is, then the result will start with cons, and the first element of this list is this here. So we take the arguments of x1 and we take the first arguments. So argov gives a tuple, and this selects the first argument. So this is the first element of the list x1. And then we call append recursively with the remainder of this list x1. This is produced by this expression. So we take the arguments of cons and we take the second argument of cons and x2. And if you want to define append without pattern matching and you do this from scratch by hand, then you would end up with more or less the same algorithm. Of course, you would not write is a cons and argov. You would give them different names, but it would more or less be the same algorithm. So this is a rather natural formulation of the append algorithm. It's also rather readable if you know what is-a, argov, and cell do. The intermediate steps are horrible, but the final outcome is, it's the easiest way of defining append in simple Haskell. So this has worked nicely. And with these rules, rules 1 to 9, you can now deal with any complex Haskell program which only defines one single function. You can have many declarations for this function. I mean, for append, we had 2 declarations. That's no problem. You can always transform it into a simple Haskell program. The problem is what happens if you have a function, if you have a program that defines more than one function. Now, assume you want to define append times plus whatever, factorial. We have no rule which deals with this yet. And that's the reason why we need 12 transformation rules and not just 9. The remaining 3 rules help us to get rid of programs where many functions are defined. So with rules 1 to 9, one can transform any complex Haskell program into a simple one, provided, so if the complex program only defines one single function. So, for example, append. It may have many declarations for this function, but just one single function. So the question is, what do we do if the program defines more than one function? And so if we have programs with several functions, with more functions, here we need some more transformation rules, and that's why we need rules 10 to 12. So there are 3 more transformation rules to come, and you need them in order to get rid of programs with many functions. Okay, so to do this, I wipe the board. Okay, so Now the first, maybe to motivate this, let's look at the following problem. Now assume we have an expression like this. So now we have proceeded like we did before. So var1 can be append. So there might have been many declarations for append. We transformed it into just one. And x1 is a simple Haskell expression. So var1 would be, var1 equals x1 would be simple Haskell. var2 equals x2 would be simple Haskell as well. But now the problem is we have many of these declarations. And in simple Haskell, you may only have one. So if var I equals xi is already in simple Haskell, we know how to do this. Then and how can we transform a sequence of declarations? So something like var1 equals x1 and then var_n equals xn. And the problem is simple Haskell only allows one single declaration. So simple Haskell only allows one single declaration and not n. So if we have, for example, a let expression like this, where we have n declarations and not just one declaration, the question is how can we transform this into an equivalent expression where you never have sequences of declarations? Any idea what we can do? Mm-hmm. Right. So this would be the first idea, doing something like this. Splitting this declaration up into a nested sequence of let expressions. So this let expression, this outermost let expression has just one single declaration here, let var1 equals x1 in some expression. And now this expression is again a let expression. Here we have one declaration, which is okay in simple Haskell, in some other thing. And then finally in the last let expression, we have var_n equals xn in some expression. So this thing would be simple Haskell. This would be very nice, but unfortunately it is not correct. So, I mean, it's simple Haskell, but it's not equivalent to the original expression. I mean, you would expect that it is equivalent, and this would be the first idea how one could do it. And we will do something like this, but only under certain restrictions. So the general idea is indeed the one that you said. General idea, split this up into nested let expressions with only one declaration. So each let expression only has one declaration. Now, let me write down an example which shows why this is not such a good idea. I don't need to write it down. I think I have it on this slide. So let's look at what this would do in an example. Now, the first thing, of course, is, well, okay, ignore this sentence down here. Let's look at this example. Now, here we have an example of such a let expression, and in this let expression we have indeed two declarations. We declare two functions, even and odd. Even should find out whether a number is even, odd should find out whether a number is odd. How does it work? Even is a function which takes the number x. If x is 0, it returns true. Otherwise, it calls odd with x minus 1. So if x minus 1 is odd, then x is even. And now odd works very similarly. It takes a number x. If x is 0, it returns false, because 0 is not odd, it's even. Otherwise, it's called even of x minus 1. And we want to know what the result of even 4 is if even and odd are defined like this. Now, this is not simple Haskell because we have two declarations of even and odd. Each declaration on its own is simple Haskell because here we only have things that are allowed in simple Haskell. But, well, we may only have one single declaration. Now, according to the suggestion that we just had, we will split this up into two let expressions. So we will split this up, for example, into let even be this in let odd be this in even 4. So the splitting would lead to let even be this thing here, blah, blah, blah. Somewhere we have odd of x minus 1 in let odd be lambda x, blah, blah, blah. And somewhere we have even of x minus 1. And the whole thing, the expression that we really want to evaluate is even 4. Now, why is this not a good idea? So this expression does not do the same thing as the expression on the slide. In fact, this expression, when you want to load this or compile this, leads to an error. This is no legal Haskell. This is no problem. This you can compile and evaluate, and even 4 will give you true. This thing will not compile and give you a program error. Mm-hmm. Now, that's not a problem. Here, so this means let even be this thing over here in this expression. So this means in this expression over here, even is known, and even is defined by this. Well, that's not a problem. This call of even is fine. The problem is this. The call of odd is not fine, because odd is undefined up here. Odd is known down here, but not up there. Here, in this let expression, odd is unknown. You can only say what even is in terms of functions that are already known. But then this even is bound down here. And in here, even and odd are bound. But this odd here is a free variable. So this is the problem. This is a free variable. So the definition of odd is unknown here. So the problem is that to do this splitting up into several different let expressions, you can do this, and that's fine, as long as the dependencies of these variables are okay. So we can say that one function or one variable, var I, depends on another function if the function calls this other function on its right-hand side. So even, for example, depends on minus, because minus is called, but it also depends on odd. Odd also depends on minus, but it also depends on even. So it can happen that functions depend on each other. Even calls odd calls even, and then we say these two functions are mutually recursive. And so what we can do is we can only do this splitting up if things look like this. So if it can never happen that a function which is defined later depends on a function. If a function which is defined earlier depends on a function that is defined later. So if var1 depends on var2, then we have a problem because var2 appears up here and it's not yet defined. On the other hand, if var2 depends on var1, that's not a problem. If var1 appears up here, then var1 is already defined, so everything is fine. So when we build this sequence, we have to take care that the recursion hierarchy is respected. This has to be a function which does not depend on anything. It may not depend on var2, var3, var4, or varn. This is a function which may not depend on var3 to varn, but it may depend on var1. And this is a function that may depend on anything. So we have to order this according to this dependence. And of course, we get a problem when we have mutual recursion, like we have it here, because here indeed even depends on odd, and odd depends on even. So what we can see is the splitting up of let expressions is only possible if, well, if you look at the slide, then var1 does not depend on var2 to var_n. var2 does not depend on var3 to var_n, and so on. So let's make this formal. What do I mean by depend? So this is definition 2.2.10, and this is dependence of variables. And I will also define what it means to separate a sequence of declarations into those parts that depend on each other. Separation of declarations. So if we have a sequence of declarations like we have it up here, so we have a sequence of declarations, var1 equals x1, and var_n equals xn. Be a sequence of declarations of a complex Haskell program and then we define this dependence relation. Then we say that var I depends on, in this sequence, depends on a variable var. So this means var I depends on var. If they are either equal, so var I equals var, or basically var occurs in the definition of var I on the right hand side. And this relation is transitive, so it's enough to have another variable var prime, so that var prime depends on var, and var prime occurs in the definition of var I. Or there is a variable var prime with var prime depends on var, where var prime occurs in the free variables of xi. So variables that occur on the right hand side, that are free variables of the right hand side, if var prime occurs on the right hand side, then var I depends on var prime. And if var prime depends on some other variables var, then var I also depends on these other variables. So it's a transitive relation. And if you have two variables, var I and var, and both depend on each other, then we say they are mutually recursive. And to write it like this, we define var I is mutually recursive to var if var I depends on var, and var depends on var I. And so then var I and var are mutually recursive. So in our example, even and odd are mutually recursive. Even calls odd and odd calls even. So if var I calls var, then var I depends on var. And well, similarly, we also define that var I strictly depends on var if var I depends on var, but var does not depend on var I. Okay, so this is what dependence means. And what we can now do, so in our example, what we can see is even calls odd and calls minus. So even depends on odd and it depends on minus. Odd depends on minus and on even. So in our example, what we would have is in the example, we have even depends on odd, even depends on minus. Minus does not depend on even because minus does not call even in its recursive call. Odd depends on even. Odd also depends on minus. And since even depends on odd and odd depends on even, we have that even and odd are mutually recursive. So this is simply looking at the recursion hierarchy, which function calls which other function. And when we want to do the splitting up of the program, then we have to decompose it into blocks, where in these blocks we just have functions that are mutually recursive with each other, and we order these blocks according to the recursion hierarchy. So we would have one block where we have even and odd. They belong to the same block because they are mutually recursive. And we have another block which contains minus, and this block would be lower in the hierarchy than even and odd because the functions from this block depend on the functions from the minus block, but not vice versa. And this separation is going to be defined as well. That is the second part of this definition 2.2.10, but I need a bit more space. So if we have this declaration, the sequence of declarations as above, P, and the sequence P1 to Pk, and these are just subsets. So this is the first subset of declarations, this is the next subset, and this is the last subset, and P1 only contains mutually recursive functions, Pk only contains mutually recursive functions, and functions from P1, they may depend on the functions from, functions from P1, they may depend on functions from P2, Pk, and so on, but not vice versa. So they are ordered. So let's say the declarations of Pi are the declarations of variable I1 equals x I1 and variable I ni equals x I ni. This is a separation of P if the following holds. It is really, if we put them all together, then we get P again. So we just separate all the declarations into K subsets, into k parts. They are disjoint, and if we unite them, we get p again. So if we unite p1 and p2 and so on, we get p again, and they are disjoint. So this is the sign for disjoint union. Next condition is they are all non-empty for all I. They only contain mutually recursive variables. So for each pi, all these variables in here are mutually recursive. So var I1 is mutually recursive to var I2 and to var INI for all I. And then if a variable from pi depends on a function from pi prime, then I is greater than I prime. So if variable ij depends on variable I prime j prime, so this is from pi, this is from pi prime, then pi must come before pi prime. So this contains variables which depend on the stuff which comes later, and this contains things that do not depend on anything. Okay, I will give an example for this and illustrate the rules 10 to 12 on Friday, and then we can see how to transform any complex Haskell program into simple Haskell, and we can then look into the next section of the lecture. Okay, so see you on Friday.